I'm here with Dr. Adrian Perrig, who runs the Network Security Group at the ETH here in Zurich. He's going to talk to us about the future of internet structures. Adrian, thank you for joining us.
Thanks for having me.
Right. We have a number of questions for you around the entire world of connectivity and how it's emerging today. What we're seeing is that there is a heightened interest in connectivity as models. And what we're trying to get to is, why do you think it's now suddenly become a central topic, something that's in the limelight now?
What's really interesting is that, given the age of networking, it's not a young field. We've been doing networking for the past 30, 40 years. That basic connectivity problems are still unsolved. On one hand, you have private networks where corporations purchase network connections within closed networks, isolated networks, to provide connectivity. But still, even with those networks, there's actually a lot of issues. On the other hand, there's the public internet, where you're using a shared network resource, also with many outages, with many issues. And so given that it's 2019 today, it's quite surprising that we're still wrestling with similar issues. Specifically, looking, for instance, at closed networks, it's often surprising to see very expensive leased lines that have actually quite poor connectivity with frequent outages, some as frequently as a daily outage. And so you wonder, how can that be, right? If someone purchases expensive leased lines, say between Zurich and Hong Kong, how can that go down, right, on a daily basis? And so the answer, which I've also learned recently, is actually quite surprising in that ISPs, when they manage their networks, they essentially attempt to manage mostly and pay more attention to the public internet, because that's where most of their customers are. However, these lines are frequently also switched over and across public connections in a virtualized fashion. And so as a result, when you try to perform network maintenance, you frequently get outages in the leased line and protected connectivity connections. And so that's actually has been quite surprising for me to learn recently, that despite isolation, despite networks that should provide high availability, oftentimes you have even poorer connectivity than on the public internet.
That's interesting. I mean, what you've just mentioned is that a lot of the time, a lot of these private networks as such get rerouted across the public internet. So what does that mean for security? What does that mean for reliability? I mean, clearly reliability is a challenge, but...
Right, but perhaps I spoke a bit too early in that it's not not that the traffic directly gets rerouted over the internet, but that they share some resources, and perhaps in some cases there are reroutings that happen based on, say, a virtualized LAN network connection that then crosses part of the open internet part of the time, while perhaps some lines are being under maintenance and so on. It's just surprising to see that pristine closed networks are not as pristine as we sometimes think, because fundamentally we cannot see what's happening underneath with the actual network packets.
But I mean, that raises another question. I mean, today with the entire, buzzword culture around the idea of ecosystems, where a set of networks try to connect with other networks, it's having a profound impact on the way we're looking at business models in the future. It's also having a profound impact on the way we actually interact with each other. What do you think people or organizations need to be doing now to address that kind of opportunity and challenge?
Exactly. So these ecosystems are quite interesting. That different entities want to get their own personal networks, right, to get higher availability. But in fact, if you look at the economic aspects also of internet service providers or ISPs, then these private networks, although they cost a lot more, they're very difficult to maintain and keep highly available. And so, based on what I also mentioned in the previous question, a better approach is actually to use the same infrastructures, right? So you're essentially you essentially utilize the existing business processes of ISPs to maintain their public internet service with high reliability, but then you use such a public network in a way that you get very strong properties regardless. And so there are new concepts, as we are going to talk about soon with the Sion network, essentially where you can have a public internet but get very strong properties, very similar to lease line type properties on a public network. And so you're surfing on this wave of economic aspects of the ISPs, yet achieve low cost and still achieve very high availability, very high performance, and very high, very low loss rates.
That's right. Okay. Well, I mean, what's interesting though is that with this entire need for, like you say, different types of networks to connect with each other, to grow their base, to improve efficiencies and scalability and everything else, there is this paradox that's manifesting itself now, which is the entire idea of, okay, we need to be more open in order to connect meaningfully, but we also need to be closed and protective about the data that we're dealing with here. How do you think an organization, banks in particular, or financial institutions, need to look at that kind of paradigm? Because it's a paradox in some.
Right, exactly. So this is a very challenging issue. Right, so for high security communication, everybody wants their own walled garden. Right? You close yourself off, you isolate yourself, but very quickly you realize, well, actually I do need this connectivity with this other entity, or I do need, there's some exception here or some issue there. And then slowly but surely you open yourself up and allow for additional connections, allow for additional connectivity, which then can bring in quite a lot of trouble, because you're now starting to mix a network that was intentioned to be sealed off and isolated, and now suddenly you have an internet connection. That's typically where security, vulnerability, security issues come in. So to resolve this issue, what we do is we say the network itself should provide internally mechanisms to provide this type of isolations. So you still have a public internet connection, but you can, within the same connection, define certain traffic aggregates that have then very high quality, very high availability properties. And so what we're doing essentially is to provide even communication guarantees across the world over a public internet. And so this is precisely how we propose how this conundrum can be resolved between these two paradoxes, as you put it.
So let me see if I've understood this correctly. What you're basically saying is there should be, or could be, a series of inbuilt ground rules that define how information travels and how it can be separated out to be saying, okay, this is hypersecure and this is okay, or is that?
Right, in essence, you're sharing the same links, which typically this is happening anyway, right? Because the same fibers frequently have multiple different types of connections. However, we're cryptographically protecting certain traffic that needs to have an advantage, and in ways that is not just encryption, but in ways that will actually provide a privilege to that specific traffic in a way that you get very strong guarantees. So if you send this one special packet, no matter what the underlying network is doing, even if it has a huge amount of congestion with traditional traffic, the actual packet that needs to get through will get through with 100% probability, or at least close to that. Essentially achieving close to a guarantee for connectivity.
You've done a lot of research into this. I mean, what does the current research sort of indicate is a way forward?
So we actually, this has been a long journey for us, because we started with this redesign 10 years ago. Okay. And initially, we purely had the goal of trying to see how secure can a network actually be built. The problem is, if you build a public internet, it's very difficult to make it actually highly secure, right? Because there are many instances in the whole world that don't get along. And just the basic question, if you have some cryptographic key that is used as a root of trust, for instance, to base security on, who has that root of trust, right? Whom are you giving this key to? Such basic questions were unresolved up until recently, when we believe we have the first clean answer that actually works in today's highly heterogeneous trust environment. And so with this, we started looking at also strong cryptographic protections, but I was always a fan of very high performance systems, right? If you frequently when you build security systems, it's hard to also make them perform well. But to the point where the systems we then designed, we started realizing that we can even get better performance than today's internet despite the cryptography. In fact, we're able to design mechanisms where routers, despite security, even get simpler than today's routers, right? And still they're performing some cryptographic operations to actually use a smaller number of transistors to do the same amount of work, yet do secure work in our case, which is kind of seems paradoxical.
It's contradictory.
This is going to be one of the interesting aspects, I believe, to mention in today's talk, because the punchline that I'm trying to deliver in today's talk is to say, look, we've designed the secure internet, but what we actually got was a more efficient internet. That even for regular communication, you're actually going to get web pages faster, the network will have higher capacity, requires lower maintenance, and so on and so forth. So
it's a big package of advantages.
Actually, this was quite a big surprise to us.
Okay, right. And why is that? Is it because technology's grown so radically? Is it because the architecture is changing? Or is this because you have a significantly new look at the way things should be? Is it a new model structure?
Exactly, right. So we have completely new ways for performing routing. Essentially, our routing protocol we've designed in a way that it's much more scalable than today's internet routing. So sometimes in today's internet you have large-scale outages, and the internet takes hours, and in some cases more than 1 day to converge until it's stable again. And our system will converge within seconds. Literally, you can perturb it, and within seconds,
we'll go back to
it just works. So it's really fundamental aspects that we've redesigned and built into this infrastructure. So that's one aspect. But another aspect that's very important is for the high availability, we have high availability built into everything. So every single aspect of the architecture, be it the way servers are reached or the way the routing works, has very high availability built in with redundancy, fast failover, and so on.
And integrity.
So we have failover times of, in some cases, of a few milliseconds, where the regular internet has failover times in the order of minutes of some simple failures, right? That's a big difference. So this availability is one important aspect. The second important aspect is the multipath system. So we have a multipath architecture, and here what this means is that instead of just using one path, you're using several paths simultaneously. And if you think about it, it's not, why should we switch to a new internet, but how come we still put up with the current internet?
One,
Because today we only have a single path, but there's so many different things to optimize for. So some connections you want high bandwidth, for some connections you want low latency, for some connections you want low loss rates, and so on. So depending on your application, you actually want different types of paths. Yet today's internet optimizes cost, and that's monetary cost. So ISPs select paths that are the cheapest for them. So it's not even necessarily highest bandwidth or lowest latency or lowest loss rates are being optimized. And so what we're doing with this in a multipath architecture, we're providing completely different types of paths to reach others. And so your application can then say, okay, so for this connection, and I really need high bandwidth. Say for a video streaming application, you want high bandwidth to push the video data through. That's usually they're quite large in size. But then when you want to do trading, where you send a transaction, those packets are usually very small, so you want low latency. And then you want a low latency path. For some others, let's say you send a recovery packet, and it really needs to get there because there's some time-sensitive aspect. You want a very low loss path. Right? You want to make sure this packet gets there. And so depending on your application, you want to select different types of paths. But today's internet
it's only one
gives you no choice, and somebody else is optimizing for you. Whereas we then said, okay, a multipath infrastructure makes a lot of sense, and then allows this type of optimizations, which we believe will lead to at least 10 to 15% faster even web page downloads and data advances in data transmission. So that's the second point.
So this leads us on to the Sion State.
Right, I'm already...
You're already on that. So I mean, you've already begun to outline what the benefits and the advantages of Sion. Sorry, please go ahead.
Right, so the third aspect, so the first one is high availability, then multipath, and the third aspect is path awareness. That the application actually knows what is the path that I want to use, because it actually matters. In some cases for regulatory compliance, you want to make sure data stays within a certain region or data does not get routed through a certain area. And this also is a no-brainer. It has so many different applications that we're still discovering new applications almost on a daily basis where this helps. It's an absolute no-brainer once you think about this, and then simply you look at this and you say, how can we still use the current internet, right? It's not the question about why should we use Sion. These are really essential features that will improve everyone's lives, everyone's connectivities. And it's self-evident once you think about it.
So effectively what you've done is looked at the way the internet has been structured or been used over the past 20 years now and completely rethought how to approach it.
Right. Well,
and that's where Sion comes in, apparently. Sion is the clean slate, or one of many clean slate approaches, but your edge here is secure clean slate approach. So why don't you tell us a bit more about that?
Right. So we specifically were thinking about how secure can we rethink network infrastructure. And this was also, I've done in my past research a lot of different works on the routing protocols for sensor networks, for ad hoc networks. I've also worked on different ways to improve the BGP protocol, make that secure. So after designing several different secure routing protocols, then the interest was, well, if we could really step back and completely rethink how would we design the optimal secure routing protocol. And this was quite an exciting journey, not always easy. We've had many properties we wanted to achieve, and initially the task seemed almost infeasible. And at some point I was thinking, okay, if we even can solve 20-30% of those properties we tried to achieve, I'd be happy about it, but we actually achieved everything. So in the end, once we had the basic idea of Sion with this a beaconing process with isolation domains and so on, suddenly the whole architecture just popped out, and we could almost instantaneously see that all the properties we were seeking popped out and appeared. And this was
the breakthrough.
Quite an exciting moment. Right? And so and then over time we just kept working on the system and kept improving it further and further.
So I mean, now that you've looked at the existing versus the future, what's your vision for Sion? I mean, what are you seeing potentially?
So what we're seeing now is, of course, security has been always one of our main drivers, but now I'm seeing and we're noticing that performance gets better, right? So we can actually even, I believe we're now looking at use cases where we're even going to lower the amount of data transmitted on cellular networks with Sion. And such things, they're going to directly translate into direct monetary benefits, right? If you look at the cost of wireless spectrum, where billions are being paid to obtain spectrum, you then, if you can save 10% of bandwidth, right, that's directly translates into huge savings. So also given the fact that with this clean multipath architecture, applications like Siri, or where Apple already ventured into the multipath case where they started using multipath TCP on the iPhone, Sion is going to make multipath a lot more powerful, right? So in Sion, you don't just have the choice of using the cellular connection versus the Wi-Fi connection. In Sion, you then get entire path choices. Okay, I want to reach a server via this path, or I want to go this way around the world, or that way around the world, or you get completely new type of path choices which no other protocol can give you today at this scale. Right.
Which gives you definitely then the efficiency advantages, but more importantly, the benefits of, like you say, scale, cost,
exactly,
security, reliability, etc. Oh.
So the vision essentially is not just a more secure internet, but actually a faster internet that gives better performance, and in a way that every user can feel it. Your video is going to load faster. You're going to get better quality for your video conferencing because a shorter path can be used for the voice. We have super fast failovers, which in video conferencing we've noticed are unnoticeable to the human. They're so fast, whereas in the internet, when an issue happens, your video conference will stall for 10 seconds, 20 seconds, 30 seconds, or simply have bad quality for a few minutes. And in Sion, all these things will be optimized away. And so given the security architecture, then that makes basic communication so much better, more efficient. Networks will have more capacity because of multipathing, because this is also very easy to explain. No routing protocol says, okay, all the traffic has to go through this tunnel and everybody gets congestion. But given the multipathing, some cars can go this way, some cars go through the tunnel, some go a bit further. But in the end, you get more capacity. And this was quite surprising for us to see. And so that's our vision, to really make it a better internet so that people don't ever look back. And the only question we hope they ask is, how come we didn't do this earlier?
So it's like making the internet a better place is a great statement, if that's what you're going with Sion. Coming to the final question here, for Switzerland, how does this all play out? What are the advantages for Switzerland of Sion's approach? Right.
So Sion provides a lot of different aspects. So we already have this, what we call an isolation domain in Switzerland, which provides very high availability for communication within Switzerland, and also, of course, higher availability communication with anyone. But what it gives us is really an isolation of routing mistakes. So, for instance, last week there was a large-scale outage in Switzerland, last Thursday actually.
I heard about it.
And also several Swiss carriers were also, and actually phone carriers across Europe were affected by this outage, where people, sometimes up to 2 hours in some cases, lost connectivity. And so with Sion, this, I can clearly say this would never have happened. Such events, that of that particular kind are completely impossible. We designed the system to even guard it against operator mistakes. Right? The system is secure against active malicious adversaries. And so you can imagine, of course, then it's also secure against somebody making a mistake. And so for Switzerland, this could, of course, mean a lot. So now our hope is that more of the Swiss economy gets involved in Sion. We can build secure routers made in Switzerland. And given the trust issues across routers, and I don't want to single out any single vendor here, they're all equally guilty, if I may say, of having huge code bases of tens of millions of lines of code, which inevitably have vulnerabilities. Right? So in Sion, in the way we are rethinking the whole system, we can afford new routers, hopefully with much smaller amounts of code, that then will provide much higher security. And so selling a router made in Switzerland, there could be a market globally, and this could mean a lot for Switzerland to contribute a new internet design to the world.
Okay, great. Adrian, I think that was, for me that was fascinating. So look, thank you very much for your time.
Thank you for all your interesting questions. Thank you.